This lesson is going to focus on a method to calculate enthalpy known as the ratio method. We use the ratio method to calculate enthalpies of chemical reactions where we already know some information. So if we already know the thermochemical equation or reaction for a particular system, we can then calculate something different about that system. So what we need to have already at our disposal or at our hands is that we have to know the balanced chemical reaction, and we have to know the delta H, okay? So you won't be able to use the ratio method unless you already have the thermochemical equation, the complete thermochemical equation given to you. And then when you do, we're going to alter something about that system. So maybe we're going to change the amount of a reactant or a product, or maybe we want to get a new enthalpy value, a bigger enthalpy value. So then how much of a reactant or a product do we need? And then we're going to compare the two. This is very similar in concept to using mole ratios, as you'll see in a second. So let's go through one example of the ratio method. It's not a very difficult method at all, but as I said, you need to have a complete thermochemical equation. So as we read through, it says aluminum reacts readily with chlorine gas to produce aluminum chloride. The reaction is highly exothermic and has an enthalpy of the reaction of negative 1408 kilojoules. So recall what this means. That negative sign right there is telling us that this is an exothermic reaction. And remember what I said in the previous slide. The only way we can use this method is if we have a complete thermochemical equation, which means I need to write out a balanced chemical reaction. Stop the video, write out your reaction, make sure it's balanced, and then come back and check your answer. So our complete balanced reaction is going to be 2 aluminums reacting with 3 moles of chlorine gas. Oops, let's fix that. Chlorine, Cl2, and then creating 2 moles of aluminum chloride. And again, our enthalpy value for this reaction is negative 1408 kilojoules. So a couple things about this information. This enthalpy value right here is only released if I have 2 moles of aluminum, 3 moles of chlorine, and 2 moles of aluminum chloride being produced. The minute I change the amounts of reactants or products, this enthalpy change is going to be altered as well. So the question is saying, what is the new enthalpy change when 1 kilo of aluminum reacts with excess chlorine? Excess chlorine tells me I don't really care about it. So what we're going to do is we're going to take that mass of aluminum and we need to figure out the new amount of moles of aluminum. And then we're going to compare it to this coefficient and create a new enthalpy change as a result. So our moles of aluminum, because we're dealing with masses, we're going to use our good old mass over molar mass formula. We don't want to use a kilo unit because aluminum's molar mass is in grams. So we're going to convert to grams. That's 1,000 grams. And the molar mass of aluminum is 26.98 grams per mole. So we're going to divide that out and we're going to get a new mole value of 37.0645. So this is a lot of moles, far more than 2, which tells me that the energy that's now going to be released when I react 37 moles of aluminum is going to be far higher, far greater than negative 1408. So what we'll do is we're going to set up a ratio because this enthalpy, again, is tied to all the molar quantities that we have there. So if I'm solving for a new enthalpy value, I would like to keep it in the numerator. So I want to solve for the new enthalpy value, which will be delta H2. This right here is my new mole value. So I'm going to just compare those two. They go together. And then I'm going to equate that to the original values. So I know my original enthalpy value here out of the equation, and I know my original mole value, which is right here, the coefficient out of the equation. So I want to solve for delta H2. I'm going to figure out that new enthalpy when I now react 37.0645 moles of aluminum. And then I'm going to compare that to the original enthalpy value of 1408 kilojoules. And that is created when I react 2 moles of aluminum. So we're going to cross multiply. I'll bring the value or the answer up here. My new enthalpy value, delta H2, is equal to negative 26093.4 kilojoules. And I have to be mindful of significant figures. So, my enthalpy value is a constant. This is my new data right here, and I got to go back to that. That's 2 sig figs. So what I'm going to do is I'm going to divide this value by 1,000, and I'm going to get negative 26. And I've just divided by 1,000. So the next unit up from kilojoules is megajoules. And you can set this up for any kind of reactant or product. When you solve for ratio methods, pretty forgiving. Just make sure that you always have your enthalpies and your moles that go together, either the before or after the changes are taking place.